Um, Thank you all for having me. I'm sorry about the last minute switch up in timing, but I'm excited I can give this talk. And I have also had a really awesome time listening to the development that everyone's been talking about in terms of open source code development and data products. It's really awesome to see so many different tools being spearheaded by the community. It really shows that everyone's dedication to open science, and so that is really cool to see. I had originally just given this very vague title, Open Science at the Onset of Next Generation Telescopes, but listening to the talks yesterday in the panel, and also taking the advice from the organizers who really wanted me to talk about sort of my overall philosophy in the design and structure of the tools that I've provided and not necessarily the tools themselves. And so in this talk, am going to give a really brief overview of sort of the development that I've done. I'm showing the logos here of Pandexo, Picasso, Virga, and Maestro, which are the tools that I've specifically been involved in and led the development of. But really, instead of focusing on what the tools do, really just focus on our philosophy in terms of how we designed them and structured them. And so my one slide into what these tools do. Pandexo is a tool that, given model, target inputs, produces a simulated Hubble or JWST spectrum. And so this is really designed to help people with proposal preparation. It's possible that you recently, in the last couple of weeks, used or were forced to use Pandexo and maybe hate me a little. But the Pandexo is now sort of incorporated into ExoCTK, which Nestor briefly talked about yesterday as well. Picasso is sort of the spectral generation piece of that. It started out as a reflected light spectra code, which sort of evolved into a thermal emission spectrum code, and then we added in transmission spectral functionality. And then you heard Anna talk about the 1D climate functionality just a little bit ago. And it also does 3D spectra and phase curves, et cetera, and spectral inferences, which people usually refer to as retrievals. And so, yeah, Anna gave a great overview of sort of the functionality included in that, and which is a great starting point for sort of talking about the design of the code itself. And then Virga, which you probably are familiar with, the Ackermann and Marley cloud code, which is used, widely within solar system science and brown dwarf science and exoplanet science. We took that original code and created a Python version of it, and so it computes 1D climate modeling and really easily and seamlessly sort of pairs to Picasso to create spectra for users. And then finally, Asan Gharib-Nezad also gave a really awesome talk and introduced the capability of Maestro, which is this open source opacity database. So instead of a tool base like the others, Maestro is a database with an online interface that allows people to sort of query, visualize, get the things that they need in order to be able to do spectral modeling or climate modeling. And so it's great that those two talks sort of went before this. They offer a great footing for what I'll talk about today. So when trying to think about sort of philosophy in terms of designing tools and making them community user-friendly products, I think it really boiled down for me into these three things. And I can't claim to take credit for having these three ideas. This is sort of well known in terms of code design. And I put a QR code to a talk that I really liked from the creator of the Keras deep learning Python tool. Um, the title of the talk is The Secrets of Productive Developer Tools, and I think it's really great if you're interested in learning more about these principles. But it boils down to three things. The first thing is figuring out how to carefully design workflows from the beginning. So this is thinking about what inputs to include within your model, to the middle, thinking about how to really design and structure functions that create really effective workflows and roadmaps for people. And then the end, which is excuse me, developing the outputs. What outputs are you actually going to supply to the user that will actually enable them to do the science? The second piece is making sure that you're providing informative feedback to users. This is in the form of warnings, user warnings, or error messages that sort of break the code and tell the user how to fix it. And then the last one is making the code easy. We all want to make our code very easy to use. We want to make it user-friendly, but we also have to acknowledge the fact that these are really complex models. They are associated with a lot of very fine nuances. We heard all these great talks about these very, physically complex things. And so we want to make sure that people can use them and access them, but that they also understand sort of what's going into them. And so a lot of people refer to this as well as reducing cognitive load. And so I'll talk about that as well. So starting in the very, very beginning, which is just the idea of deciding what the inputs and outputs, what inputs are for your code. If I think about Picasso as an example, the user on the user who goes to take that tool really just wants at the end of the day a spectrum with associated error bars. But if I think about all of the things that I need to know in order to compute that really seemingly simple data product, it's quite complex, right? I need to understand the target parameters. I need to understand what the user wants in terms of the calculation simulation parameters, how they want the normalization done or the background level, how they want the noise model to actually be computed, and then all of the things associated with the instrument setup, the modes, the filters, the apertures, dispersers, JWST and Hubble are sort of complex beasts. A user would have to really specify the detector setup and then tell me how they want the extraction strategy done. And so the first piece of designing open source code is really knowing your audience. And the reality is, for Pandexo at least, most of my audience really don't care at all about all these different parameters. They are likely up against a deadline, have to submit a proposal in 15 minutes and just want out their spectrum. And so the first thing that you really have to ask yourself in developing code is sort of, what choices do I need to force people to make versus what choices can I safely make for people? And so if you look at sort of the instruction tutorials for running Pandexo, you can see that when a user goes to specify an instrument, they just have to set up these two very simple parameters, tell me that you want a near-cam simulation followed by the filter name, which we've boiled down to this figure that is shown on the ExoCTK Pandexo calculation website. And so this figure sort of boils down all of these different complex choices into a series of maybe 11 choices that you need to make in terms of what instrument you want, what filter or grism, and those choices you can simply print out with one of these Pandexo functions. And so what a user doesn't realize is that by simply specifying this string of two things, you trigger this massive this massive configuration file, which defines all of these sort of complex choices that we've made on the back end for you. We think that they're sort of the best choices to do a near cam filter observation. And then what we do is after we make these choices on the result end, we give you back this nice machine readable table of inputs that include all the necessary things that you need to make an AP to create your APT file. And so this is a way of sort of reducing the amount of inputs that a user needs to have, while also telling them on the back end sort of what you've done for them. And so they can sort of go about their merry way and submit their proposal in the next 10 minutes. And so once you decide what inputs are relevant for you, you then have to think about your functional roadmap. Now, taking Picasso as an example, a user might have to specify a set of chemistry parameters, climate, clouds, and then once they have that, specify, whether or not they're doing transmission or thermal emission or maybe brown dwarfs, reflected light. There's all these different complex choices, these different roadmaps that someone can take when they're interacting with your code. But at the end of the day, really all Picasso is a spectrum function, right? Given a set of climate parameters or atmosphere parameters, planet parameters, etc., give me out a spectrum, which is an x-axis and a y-axis, and I really need those two. Really, just at the end of the day, you could think of just needing those two very simple parameters. And so this is sort of, I know when I started working with Fortran-based code, this is sort of what things looked like. You got out this function with dozens of different inputs. The doc strings were very long. You read through it, sort of built out your function, hoped that you got everything in the right order, and sort of called it a day. But with Python and object-oriented programming, we can sort of switch this and create these sort of intuitive roadmaps that sort of bundle different objects. And so if you look at these different inputs, we can see that, some of them have to do with the atmosphere, some of them have to do with the planet parameter that sets the gravity, for instance. Others have to do with the star itself, or maybe the orbit parameters. Some are all associated with the cloud, and then the others ones describe sort of the calculation itself. And this is sort of just a simplified version to give you an idea. of how you can start thinking about grouping your different input functions. And so this is just a teeny window into sort of how object-oriented programming works in Python, where we start out by having the user specify a simple little input bundle. And then you can go through and start packing on these different things. So then the user specifies gravity if they need to, the stellar parameters if they need to, the atmosphere, the clouds if they need to, et cetera. And this sort of creates this functional roadmap for someone that is much easier to navigate than sort of setting a massive function and having just one function that controls everything within your code. Now you might think, I've done this, it works out, I've sort of told people how to create this, and oftentimes actually that's not quite enough. And so if I think about Picasso and all the different ways that someone can interact with this code, there are many different ways. And what we do is we try and provide a tutorial for each one of those different pieces of the code. So if a user is interested in computing transmission spectra, we make sure to have an individualized tutorial for all of the basics of transmission spectra. Similarly, for thermal emission, we have one tutorial set for thermal emission with exoplanets and another of thermal emission with brown dwarfs, recognizing that an exoplanet scientist's needs are going to be very different from a brown dwarf person's needs. And so we have to make sure that we're thinking about creating two different roadmaps for those two different groups of people. Similarly, with reflected light, coronagraphy is very different than someone doing transiting science, and then cloud modeling, and you kind of get the picture. And so I think if I were to think of a certain motto that we have within our team, it's really, we have a tutorial for that. We really try and make sure that for every single new functionality that we build, or for a specific niche within our larger code base, we have specific roadmaps to bring users really just to the things that they need within the code, even if it means being slightly repetitive. And then the last piece of this is just deciding what outputs. And you might think, why is that so difficult? They just need a spectrum. Why can't I just supply someone with, their RP over R star squared for transit and a wavelength array and call it a day? And the reality is that there is a lot of metadata that our models build up when computing something like this. Some of that metadata is things that the user has supplied. Some of the metadata is things that you have sort of accumulated within creating a calculation for someone. And so the types of model outputs that we have, even for one little thing as simple as a spectrum code, are really complex. You can have different kinds of spectra, chemistry input, climate input, cloud input. If you're doing retrievals, you likely have some form of posteriors. And so we really have to sort of think carefully about what do we want to actually supply users so that they can do their science. And I think a really interesting case of this is the JWST transiting exoplanet early release science. I'm just showing here the 4 spectra that were released through this analysis, the near spectrum, the near cam spectrum, and then the 2 near spectra with G395 and then the prism. And what I think is really interesting, if you go through these papers, if you look at the NearCam paper, they chose to show the spectrum with this plot of the tau1 surface pressure level to sort of show what pressure these different molecules were absorbing at. If you looked at the JWST near-spec prism paper, they chose to show the spectrum with sort of the individual optical contributions from each of the molecules. And then if you looked at the near-spec G395 paper, they chose to show the spectrum with individual molecules removed. And so I thought this was incredibly interesting. These are 3 different use cases of Picasso being utilized to analyze the spectrum, and these 3 different subsets of teams are choosing to utilize different versions of the model output to showcase different parts of their analysis. And I think that's very interesting and sort of gets at this idea of sort of thinking about what you need to include so that a user can do sort of the science analysis piece, which is really sort of a lot of times the most interesting piece of the modeling. And so when thinking about what, deciding what outputs to use, it's really important to sort of, one, make sure that you're avoiding any sort of metadata information loss after the calculation is done. I think we've all run into that scenario where you return to a file that you created a month ago because someone is asking for the WAS39 spectra, and you realize that you don't really remember what inputs you created. You're pretty sure that it's the right thing, but there's not really any way to be sure. And furthermore, if someone was trying to do a model intercomparison with you, it would be very hard to sort of tell them what were the ingredients that went into making the sausage, right? And so it's important to sort of bundle all your outputs together and make sure that you're really keeping track of all of the necessary metadata needed to reproduce that calculation sometime downstream. The other piece is to make sure that you have storage formats that are really informative and intuitive for other people to use. During the JWST Transiting Exoplanet work, we were constantly passing files back and forth, checking and cross-checking things. And so in doing that, we developed this model storage best practices, which is available as one of our tutorials. It sort of goes through different model formatting styles, standards, and specifying units. We chose at the time to use Xarray, which I think is a great model output storage format, and I encourage you to check out the tutorials. And we even we had standards for how to name files, and we even had functions to sort of check that certain data was in compliance with what was needed to sort of reproduce that calculation. And so this sort of model storage best practices, I think, is very important and should be sort of dealt with on a community basis. And then the last piece is, once you've created this really nice, metadata bundle, you have to make sure that your user base has a way to explore it. And sometimes that's not intuitive, especially when we create these, massive JSON files with, many embedded keys, for instance. It's sometimes hard for people to get to where they need to go. And so in all of our code bases, we provide, our code that to just go through this, mostly in the form of various plotting functions, is really extensive. We have, thousands and thousands of lines of various plotting things that people can do to plot, to analyze their model outputs, and those are all also created or available within the documentation itself. And so those are all very important aspects of sort of deciding what outputs to use. And so in terms of designing workflows, thinking carefully about what the user must input, making sure that you're creating roadmaps for each code functionality, and then establishing outputs that really avoid information loss and really enable sort of explorable content, reproducibility, collaboration, that sort of thing is incredibly important. And the next piece that I want to talk about is the providing informative feedback to users with warnings and error messages. So we've all ran into the scenario where we stumble upon a code error that is impossible to interpret. We don't really know, in this example, I'm showing some file is missing. I don't really know what file that is. I'm not really sure why it's even pulling that path, and I don't know how to fix it. And so in developing code, it's really important to sort of anticipate the pitfalls that your user base might encounter and make sure that you're raising errors for people instead of just whatever the native, Python package error message that a user might be subject to. So one example of this is developing these, is the environment variables. And so in development of Picasso and Pandexo, actually, one of the most frequent problems that people have was just specifying an environment variable, which you might think would be an easy thing, but it often gives people lots of headaches. And so I would get emails often asking, why a certain thing, why a certain path wasn't set, and that sort of thing. And so I have now these, an error message that checks to make sure that a path exists, which is a very simple thing, and then tells someone, you probably haven't downloaded seller reference data, for example. You can follow the instructions here to fix that problem. If you think you've already done that, then maybe check this. And so it sort of gives people not only a way to understand why they're encountering a problem, but also tells people in what direction to move to next in order to fix the problem. And that is an incredibly important piece of creating open source tools. And I just want to say that I'm still constantly finding holes in the development of my code where I need to enforce new errors, because it's really tricky to anticipate all of these different pitfalls that someone might encounter. An example recently was a student who wasn't just encountering nans in a spectra, and it turned out to be that somehow they had found a workaround to sort of avoid the errors that I had put in place, and so I have to make sure that I don't just tell the student how to fix it, but I actually take that feedback and incorporate a new error message such that that error never gets encountered again. Or, I mean, if it does, someone now knows how to fix it and doesn't have to contact me directly. In addition to just straight coding errors, especially when developing physical codes, it's really important to enforce, to create guardrails for people so that they don't enter in non-physical regimes. All of our codes have limitations. That's just the nature of these physical models. One example in the development of our cloud code Virga is the sort of chemical limitations in terms of metallicity and mean molecular weight that we have to make sure that users don't encounter or don't go to. So, for example, if you go to our documentation, we actually provide users examples of what not to do. So here's an example of a user setting metallicity that's too high, and the error message says, hey, you're in a non-physical regime. Please contact your local theorist to determine what to do next, because we really don't want people to go down the rabbit hole of trying to compute a calculation in this regime, even though it technically would, result in a non-nan number. But sometimes it's a little bit more difficult to decide sort of, what is an error, if you should really enforce an error or something, or if maybe you should think about maybe just providing a warning instead. And a good example of this, I think, is in the development of our Maestro community database. Our main goal in this database that Hassan talked about earlier was to make sure we were providing opacities for all relevant molecules for all relevant pressure temperature combinations. But in a lot of cases, no data exists for some combinations. So for example, in a lot of cases, there's no hydrogen line widths. In a lot of cases, there's no high temperature line lists. But we still think it's important to provide anything, and we can make informed decisions to give someone something that's better than nothing. And so, but these nuances are very important. And so the way that we've dealt with this in our online database is that we have a set of standard calculation cautions that pop up for each data bundle. So in this example, a user is trying to query C2H6 at 900 Kelvin at a bar. It seems very reasonable, but there wasn't at the time, or isn't, an exomol high temperature line list, and we're using HyTran instead. And so if you go to the list of calculation cautions, you can sort of see this caution that's associated with that data product that says, hey, the line list used is not suitable for the temperature regime. And it's not meant to tell people not to use the data. It's just really meant to provide sort of intuition in terms of, more information that people can use to carry on to their analysis, be cautious of sort of how data was created or how a model is being conducted. And I think there's similar examples of this in many different facets of model development. Okay, I know I only have a few minutes left. The very last piece of this is just trying to make models easy without removing these nuances like I just talked about. And I think an example of this is that I like to give is the scattering and radiative transfer. So conducting scattering and trying to do, model clouds and in scattering atmospheres is very difficult. It can, go from a single parameter if you're just accounting for extinction to like many parameters if you're thinking about all the different complex scattering multiple cloud layers and scattering properties of your atmosphere. And furthermore, there is all of these different nuances in terms of how to do phase functions. So some people choose isotropic phase functions, other people choose pure Rayleigh, other people choose asymmetric phase functions, other people choose some combination thereof. And so it's really important to make sure that a user can really, simply do a cloud model, but we don't want to inundate them with these choices right up front. And so what we do within Picasso, where we do have many different options for all of these different scattering choices, is we have a specific tutorial dedicated to just code approximations. And we make it really easy for people, once they've done their calculation, to sort of filter through all these different choices and try and understand how that affects the spectra that they've computed. And so that's one way of sort of making it easy, but still, forcing people to sort of think about the choices that they're making in doing modeling. But you don't want to make it too easy. And so another example of this is also within sort of the cloud code Virga. I created a function to try and help people select what cloud condensates to include in their model. Very simple. If a certain cloud condensate crossed the condensation curve, it would notify you that maybe you might have that cloud deck. What I didn't realize is that I was completely eliminating the need for people to actually think critically about how they were doing their modeling. And in some cases, users were inputting these pressure temperature profiles that extended to really high pressures. And my model was telling them, you should model, a dozen different cloud condensates, and that led to really unphysically high optical depths at high pressures. And so now I guide people to sort of pick a subset. And actually, in making this talk, I realized I probably could use even more documentation surrounding this. And so I'll have to go back to doing that. And so those are sort of the main principles, I think, in terms of the philosophy and design of the tools. And I just want to say two last quick things in terms of developing open source tools. This is actually two helpful pieces of feedback that I got from a rejected open source proposal, just to speak candidly in terms of things that I didn't really think about that I think are now very important. So one piece of feedback that I received early on was, I had clearly described how Picasso directly addressed the goals of NASA SMD and how the code was being used in the community, but Picasso as an open source object does not have significant usage in the NASA community. And this is something really important about the development of open source tools, is that you should really be thinking early on about how you're going to measure impact and the success of your code. And I didn't really think about this early on at all. In fact, I really wasn't keeping track of any metrics. Since then, I've now started keeping track of Zenodo downloads and GitHub clones, and we have Google Analytics on our tutorial pages, making sure that I'm keeping track of papers that Picasso uses, workshops where it's implemented in coursework and that sort of thing. But the earlier you do this, the better, so that you don't miss out on some of that information. The next piece that I think I was actually horrified to see is that they said no contributors beyond the proposal team have contributed to this repository. And I was horrified by that because there were so many people that had contributed to the code, and somehow I wasn't showing that. And so I came upon this really awesome tool, which is allcontributors.org. This is a specification for recognizing contributions to open source projects in a way that rewards all contributions, not just specific code contributions. So if you go to allcontributors.org, you can see this really nice sort of emoji key format that sort of shows all of the different ways that people can contribute to code. And through this bot, you can sort of keep track on all of the contributors to your repository. And I think that will help showcase funding agents, how many people are actually contributing to your repository, even if there's only a smaller subset of people who are actually contributing the code. And I am completely out of time, so I will just end by thanking all of the awesome contributions that I've received to these code bases, and I'd be happy to take any questions.
Thanks, Natasha. We have a question from the chat really quick. This question is just a comment. The NASA planetary spectrum generator has a lot of flexibility in simulating transmission and reflection spectra based on telescope detector, scene geometry, atmosphere, other things. It can also do retrievals. The question says, why do many external groups still develop their own codes instead of working with Goddard to improve and enhance their code? So I guess what are kind of the benefits of making these alternatives to other codes of the community?
Yeah, it's a great question. So PSG is a great tool. All of these, like a lot of the tools that I'm showing here, for example, Picasso and Pandexo, were developed around the same time as PSG. And I think you'll find that a lot of open source tools, and I think I might have a slide of all the different open source tools that exist, but a lot of these open source tools were sort of developed concurrently. And so just because someone was sort of first to market, or maybe it seems like, it's been done, or the tool already exists to do something, and you're sort of the holder of a code that also does that same functionality, you shouldn't be necessarily discouraged from open sourcing your own code. Like I showed in all of the assumptions that go into creating codes, all codes do something different and have a different approach to doing these. They all come with their own nuances. And it's incredibly important that we have validation across several different codes, even if they do the same functionality. And so, for example, for the early release science team, there were, in addition to like Eureka, which you heard earlier today, there were 10, 12 other different reduction pipelines that were used. Using so many reduction pipelines were incredibly valuable to sort of understanding how to do JWST reduction. Similarly, for the code development, in order to analyze the spectrum, it wasn't just Picasso that was doing that spectrum generation. There were maybe half a dozen other codes that were used to do that sort of atmospheric generation as well. And it was similarly super important that we had validation across several different codes. And so to answer your question, um, it is code overlap is a good thing. And no one should be discouraged from necessarily like reproducing or producing a code if you think it's sort of been done already.
Thanks, Natasha. Anyone else who has questions, please type them in the Slack chat.